And I have to warn you that I have to leave right after this talk, so I'm going to grab my bags and just rush out. So if I'm getting overtime, just let me know, because otherwise I'll stick around for longer. Today I'm going to talk about actually orbital magnetism. And in our community, perhaps, and in this conference, this comes a little bit as a surprise, because we have seen many successes in this workshop and in this event, which relates to different aspects of spin physics, such as exotic materials, skyrmions, ultra-fast spintronics, not so much topological in this workshop, but also antiferromagnetics spintronics has been quite well represented. And most of these phenomena that we have seen, they actually require some spin-orbit interaction or are based on spin-orbit interaction. And among the most fundamental effects that you know, which come from spin-orbit interaction, is the spin Hall effect, anomalous Hall effect, and also the effect of the spin-orbit torque. The spin-orbit torque, as we know, comes from spin-orbit interaction in systems with broken inversion symmetry. And there we apply current, and we can exert a torque T on the magnetization, which is able to shift it. Works very well for ferromagnets, works very well also for antiferromagnets. And normally we distinguish several mechanisms, of which one of the main ones, as we know, is the generation or injection of spin Hall current into a magnet, where the spin current interacts with the magnetization and changes its direction, or due to creation of some current-induced magnetization at the interface or in the film. Spin-orbit torque by now is quite a developed field, and you see there are a lot of material applications, a lot of devices which can be based on it, and there are a lot of complicated physics which evolves around it. And if you look around at this map, you will realize there is one thing which comes a little bit kind of surprising, and that is due to the orbital physics. What we know about orbital magnetism is that this is something, or one of the things about orbital magnetism, there are many manifestations of it, is due to the motion of electrons around the atomic cores, which also couples to spin by the spin-orbit interaction. This is basic stuff, and everybody knows that. In crystals, the crystal field normally forms these orbital groups which have zero orbital momentum, which then the spin-orbit interaction is able to split into states of polarized up or down. And then in a ferromagnet, for example, you can partially occupy some of these states, and you can achieve some orbital magnetization, also basic stuff. The effect, in bulk at least, is normally quite small, and therefore it is not clear whether it is good for anything. Moreover, as a theoretician, if you look around, you will realize there is an enormous effort which is trying to bring orbital physics onto the level of some formalisms which are rigorous and which do not rely on this position operator evaluation of your electronic motion, because that's not a good operator, does not give you good things. So is it actually worth it? Why would we work on what we call orbitronics? And one advantage, one of the main advantages, comes when you look at the weaknesses of spin-orbitronics, and that is the strong spin-orbit interaction. Many of the effects that we know, so we normally use platinum or some F-electron systems, for example, where we need strong spin-orbit interaction to promote the effects that we are looking at. Of course, that is not very good, and actually many of the beloved in spin-orbitronics materials belong to this European Union's critical raw materials list, so there are not so many, there is not so much of them actually in nature. While orbitronics, on the other hand, does not rely on spin-orbit interaction. And that is very nice, because it leads to sustainable electronics, so we can use lighter elements to promote very strong orbitronics effects. Moreover, if you compare, for example, in this table which Aurelian made, the spin transfer torque, the spin-orbit torque, and the orbital part of the spin-orbit torque, you will realize that orbital torque can exceed or can outperform the normal torques that we are used to also in this workshop. And this particularly concerns, for instance, the energy efficiency. So how does that happen? And I will try to promote a couple of points about the orbital magnetism today. First of all, as I said, is that it doesn't have it doesn't need spin-orbit interaction. Second one, try to outline the mechanism for orbital torques and show how this can give you increased energy efficiency. I will try to also make you aware that orbital currents can be actually quite long range as opposed to spin in ferromagnets. And finally, orbital motion couples naturally to the lattice and thus to phonons. And that's, of course, very nice, but also I'll try to underline that it can also couple to magnons. And all these magnonic applications that we have seen, in principle, they can carry a cloud of electronic orbital momentum with them. Okay, let's start with the first one, and for this, let's take a look at a surface of some material, for example, bismuth silver or some Rashba surface. If we take a look at an electron which propagates with Bloch vector k, and let's say it has an orbital momentum which is perpendicular to it in the plane, then what you can show is that the wave function of this electron will develop an electric polarization out of the surface of this type, and this will naturally couple to the electric field that is created by your surface gradient. And this will lead to the energy splitting between orbitally polarized states. And you can actually demonstrate this quite nicely, for example, from first principles calculations like bismuth silver surface, where you see the splitting between orbitally polarized states already without any spin-orbit interaction. And the magnitude of the effect here is not driven by spin-orbit. It is actually driven by the crystal field. So it is a large effect. What we name this effect is the orbital Rashba effect, because it looks very much like the normal Rashba effect, only with the orbital Rashba constant in front of it. What is nice is that the orbital Rashba can create these chiral textures of orbital moment in the reciprocal space. And what is also something you realize is that, in principle, the magnitude of this local orbital momentum of your Bloch electrons can be much larger than that given by spin, like 1/2. So more than that, you cannot go. In orbital physics, you can go much larger than that. But if you have these chiral orbital textures, of course, the most natural thing to do is to apply a current to change the occupation of your left and right movers, and therefore promote what we call an orbital Rashba-Edelstein effect or orbital Edelstein effect, or as we like to refer to it, it's the current-induced orbital magnetization. Of course, you will argue, okay, this is a bismuth silver that I took, but let's take a look at a much simpler system, a much lighter system. It is an oxygenated copper, where we take a slab of copper, we're simple theoreticians, we model everything in simple terms, we deposit a layer of oxygen on top of it, and we look at what happens. So what happens is actually quite surprising. You realize that the PD hybridization between copper and oxygen atoms drives a gigantic orbital Rashba effect, and this leads to very large orbital polarization of your states in the vicinity of Fermi energy. So what we do next is we apply an electric field in the film of our system, and we look at the current-induced orbital polarization. That's the orbital Rashba Edelstein effect, and we look at the orbital Hall effect. That's the orbital velocity which propagates along the normal to the film. And what you realize is the magnitude of these effects, it's truly gigantic. In comparison to spin, for instance, this becomes immediately obvious because spin is scaled by a factor of 10. And if you compare the magnitude of the orbital Hall effect here, you will realize that it is as large as the spin Hall effect in platinum. So there are many nice things that you can do with this. However, I have to focus a little bit, and in this talk I ask a question, whether we can actually use these orbital things, and we can harvest them for manipulating the spin properties of our materials. Okay, let me boil it down to some simple picture. So we all know many things about spin-orbit torque. So what is this orbital torque? And for this, let's take a look at the beginning. So what we want to do is we want to manipulate the direction of an exchange splitting between the electrons in an atom, right? That is something that we describe as an exchange field. Now, the only thing which couples to this exchange field in your Hamiltonian is the spin of your electrons. The orbital moment does not couple directly to the exchange field. However, of course, you can influence the spin of your electrons by the orbital magnetism, by the spin-orbit coupling. In particular, if we will have orbital and spin somehow misaligned in our system, then there will be some coupled dynamics, and this can lead to a torque in a way similar to that we have with spin Hall effect. For the spin Hall effect, we generate a spin current, we inject it into a ferromagnet, and it interacts with the magnetization. In the mechanism of what we call orbital torque, which is part of spin orbit torque, only it is hidden in there, we generate an orbital current, for example, by the orbital Hall effect. It is injected into ferromagnet, it interacts with the spin of electrons there, and those guys act on the exchange field and thereby are able to change the magnetization. Well, I can present you many calculations, but I take again this magic copper oxide system where in the couple of years ago, together with the Chloe group, we took platinum, we deposited on it the TIG, which is an insulating ferromagnet, and we measured the torque. And the torque was very nice. It was what we would expect from spin Hall effect of platinum. On the other hand, after that, we deposited a layer of this oxygenated copper, of course, not expecting any change in the torque, because it's a really stupid material with no spin-orbit interaction. However, what happens is an increase in the spin-orbit torque efficiency by a factor of 16. If you ask me, it is a gigantic factor, and you probably don't believe it if you see it. What happens here is that this magic orbital current that we generate at the copper-oxygen interface, it is injected into platinum. There, it is transformed into spin current, and this spin current is injected then into our ferromagnet. So this is quite amazing, and this comes together with another twin, what we call an orbital Rashba-Edelstein magnetoresistance. Of course, what happens here, and that's in another type of system, is that we inject an orbital current into a ferromagnet. In this case, it's a permalloy. And depending on the magnetization direction, it will either reflect from the interface or it will be absorbed by causing a torque. And this will influence your longitudinal resistance pretty much in the same way that we have in the spin Hall magnetoresistance. And again, if you explore the thickness dependence of this effect, you will see that you will actually have to assume that there is a gigantic orbital diffusion length in this permalloy. Something which when you compare it to spin properties is actually quite surprising and completely unexpected. So what happens here? And for this, let me turn to the orbital physics in ferromagnets. And in ferromagnets, everything can be much more complicated. So in ferromagnets, we have additionally a magnetization with which we can control stuff. So we have these orbitally polarized states, and when we switch magnetization, the orbital polarization will follow your magnetization. So these orbitally polarized states, they will have to cross somewhere, and these are these special points that we call the wild points or whatever. That is not important, and they often occur at the phase boundary between topological phase transitions. And what is interesting is that if you evaluate the orbital response in the vicinity of such points, you realize that it can be quite gigantic. And the nature of this response, the sign and the behavior around these points actually points you to the nature of this. So you can say a lot about the nature of these points. As thus, we have also predicted that this current-induced orbital magnetism can serve as a marker of your topological phase transitions. In the same chain of works, however, we have also calculated the spin-orbit torque in these materials, realizing that the same points cause very large spin-orbit torques, which can be actually truly large and can exist even in insulating materials. And it is only this year that we have realized why this happens, and for this, let's take a look at what we call continuity equations, which we can write down for the density of orbital angular momentum and spin angular momentum, and they are actually quite simple. There are two basic terms which take part. One of them is the influx of angular momentum into your system, and the other one is the torque with which we can lose orbital momentum. So let's take a look at the spin part of this equation. And the torque here consists of two parts. One of them is the exchange torque. That's the one that we're looking at. That's the one that we measure experimentally. That's the interaction of the spin of your electron with the exchange field. And the other one is the spin orbit part of the torque. That's the interaction of the spin of your electron with the spin orbit potential. And this spin orbit torque, spin orbital torque, enters on equivalent footing into the equations for L and S, and thereby can transform currents between each other and ignite generally coupled spin orbital dynamics. If you assume a chain of approximations, you realize that the spin orbital torque can be written in this intuitive way that I have presented in one slide, and it can ignite this coupled dynamics of spin and orbital angular momentum. Now, if we work in a thin limit of a two-dimensional system, there is no influx of spin current out of nowhere, and that means that in a steady state, the whole torque is given by the spin orbital torque. So in two-dimensional materials, you can forget spin currents, and you have to start thinking in terms of orbital angular momentum. Of course, in reality, it can be complicated. So if you have layered van der Waals materials and so on, there will be a flow of spin angular momentum as well, as we have also shown, for example, for FGT system. However, the orbital physics becomes extremely important for this type of materials. Now, there is one more exciting point about this degeneracies, which leads to what we call long-range orbitronics. And let's take a look, for example, at the crystal splitting of our states on a cubic lattice T2G electrons. They are split a little bit by spin-orbit interaction, and by tuning the magnetization direction, you can somehow exchange this. Now, what I do is I create a state which has an Lx of +1 at time equals to 0. And then I follow the evolution of the state in time, and what I observe is a very slow decay of orbital polarization. This is quite surprising, and this is in contrast to spin, because our spin experiences exchange scattering as it enters the ferromagnet, while the orbital angular momentum will then decay over much longer distances. And you can actually do some calculations to show that this is indeed the case, and you can have this physical decay of orbital polarization over very large distances, and you can show that it indeed comes from these band degeneracies in our system. Now, this leads to very interesting spin-orbit torque physics, because if we start integrating, or if we start increasing the thickness of our ferromagnet, we will realize that this orbital torque, it actually doesn't reach a plateau for a very long range of thicknesses. And in fact, if the spin flux torque reaches the saturation quite quickly, it can lead to a characteristic long-range decay or increase of your overall torque of the film as you increase the thickness. And in this particular case, it can even change the sign. And this is surprising. This is quite remarkable. This is also something that we have observed with our experimental collaborators, the group of Kazuyo Ando, where you see this increase of the spin-orbit torque efficiency in this very light system with the thickness of nickel. And this comes as quite a surprise to people who work in spin-orbit torque physics. This is something completely unexpected. The decay lengths of orbital currents in ferromagnets that we can predict are of the order, in some of them, of course, not in all of them, you have to have proper electronic structure, are of the order of tens of nanometers. And the orbital hole scattering angles are also can reach as much as 50%, something which you have to look for in spin orbitronics. The scaling properties are also very exciting, so they do not follow into this intrinsic or skew scattering kind of scaling that we expect for anomalous Hall effect or for spin Hall effect. And generally, we understand very little about the scattering theory of orbital angular momentum. In the last part of my talk, and if I have very little time, let me know, I will try to also outline the fact that ferromagnets do not only have all these nice properties associated with orbital physics, but they can also be complicated because they can be non-collinear. And when things are non-collinear, we have known for some time that there is a special flavor of orbital magnetism, which we call the topological orbital magnetism, which is due to hopping of your electron around the triplets of non-collinear spins. This type of orbital magnetism is proportional to the chirality, it is proportional to the lattice, and the strength of it is given by what we call a topological susceptibility constant. It is a solid effect. It has been calculated in many materials. It is difficult to explicitly take it out of your measurements, for example, from XMCD. However, we are still working on it. But we're quite confident it is there. It can be very large, and it can mediate many things in noncollinear magnets, such as, for example, novel types of exchange interactions. Read more around in the papers on this topic. Now, let's take a collinear magnet, and let's send a magnon there. Yeah? So naively, we would think that, in principle, nothing should happen, so the chirality should not be created. But this is only true for a square lattice, or for a lattice of a very high symmetry. If you take a lattice which is triangular, honeycomb, or Kagome, for instance, and you include the effect of either magnetic field or DMI or both, you will realize that if you use some simplistic models for describing this spin wave physics, and if you look at the chirality that the Magnon band can carry, you see that, for example, already in a ferromagnetic Kagome lattice, you have a finite chirality of your magnonic states. So you send a magnon in your system, it has a net scalar chirality, which you can feel if you're looking at this magnon. This is true not only for ferromagnets, but even for Kaplaner antiferromagnets, such as manganese-3 germanium. Now, when you increase the temperature in your ferromagnet, you occupy more and more magnonic bands, which have curvature, which have chirality, and thereby you're able to create or increase or suppress the net chirality in your spin system. And of course, your electronic magnetism, as I said, it is very sensitive to this. It reacts to this. It feels this chirality. Let me try to convince you quickly that maybe there is a hint that this is actually true, because if it is true, this would be very nice. What we did in collaboration with our experimental colleagues, the group of Peng Li and Wei Zhang, we took a system which is copper 13BDC, which is a prototype topological magnonic insulator. It has 3 bands, and it has this churn band gap in the middle. And if you look at the chirality of these states, you see it is there. So what we do next is we take each magnonic state, and we evaluate what is the effective electronic orbital moment that this magnon can create. And by having an estimate on the constant with which chirality reflects in orbital magnetism, we're able to estimate the behavior of this orbital magnetism as a function of the direction of the magnetic field in your system or the temperature. And you can look here, and you see the magnitude is not very large, but what is interesting is that for the out-of-plane field, you have an increasing orbital magnetism with temperature. And this is quite counterintuitive, so we proposed that magnons here actually would drive more magnetism as you increase the temperature. And what we did is we looked at the G factor, which, as you know, is proportional to the orbital magnetization in your system. And guess what? That is exactly what we observe in this system. What happens, what we predict. So for low temperatures, we have here everything is driven by local spin-orbit physics, which is very small, nevertheless. However, it diminishes as you increase the temperature. But for the out-of-plane field, there is a clear increase in the G factor, which points to the fact or hints that this orbital magnetism could be actually true. I think this is good news for all of the magnonics people sitting in the audience or who are already elsewhere, because that means we can actually do many things with orbital magnetism using magnons. For example, we know that we can excite currents of magnons, and we can have transverse currents of spin associated with scattering of magnons in DMI systems. And in fact, we can also suggest that the same should happen with the orbital angular momentum. That's what we call orbital Nernst effect. So you apply temperature gradient, and you have a transverse current of orbital angular momentum in your system. This is a very nice effect, which is very sensitive to topology of your system and can be very large, obviously. Otherwise, I wouldn't be talking about it today. What is also interesting, if it is true, is that it can also drive orbital magnonic torques. So you can use magnons to inject orbital angular momentum, not only spin into the magnetic systems that you study. This is, of course, something you either see, but you don't know, but it would be nice to have an explicit measurement of this, and I hope maybe some of you will be interested in doing that. Okay, So I come to an end. I think it is really time. And just a couple of words about the topic. We know that orbital magnetism does not need spin-orbit interaction. However, we still have a handful of systems where we have demonstrated this gigantic orbital torques and large penetration. So there is really need for more material design of orbital emitters, if you wish. Obviously, orbital transport properties are truly fascinating, but as I said, we're still missing fundamental understanding of orbital scattering properties, and here we need to apply an essential effort. Orbital magnetism is at the cross-section between spin, phonons, and magnons, as you have seen, and therefore, it is a very nice variable which can link different phenomena together and which can let you transform one into another. And here also, like excitations which carry naturally orbital angular momentum can help you, laser pulses, vortex beams, or even acoustic waves. Okay, so my acknowledgements. Most of this work has been done by outstanding Dongwoo Go, but also by Frank Freimuth, Fabian Lux, Li Chuan Zhang, Tom Saunderson, and there is a bunch of people which have been involved into this effort. Kazuya Ando and Shilei Ding and Gerhard Jakob, Olena Gamonai, Stefan Blugel, and so on. And in particular, our experimental collaborators, I have to thank. That's the lab of Matthias, Jimbo Young's lab, Byung-Guk Park's lab, and Kazuya Ando's lab, which have been extremely helpful and exciting to collaborate with. And I thank you for listening to this talk.